Hello, everyone. It's Dan Sannig from ICLR. Thanks very much for joining us for our first webinar of 2018. We're very happy to have everyone on the line, and we're happy to have our speaker, Andrew Wiens, here as well, who actually is presenting remotely from Calgary. A couple of notes before we get started. As with all of our other webinars, we'll be taking questions throughout the webinar, and we'll have a discussion period at the end. To ask questions, you can use the question and answer function that you should be able to find in the top left of your screen. If you're on a PC, if you're on a Mac, I think it's in the bottom of your screen. So we'll collect all the questions throughout the webinar and have a discussion afterwards. Just a quick introduction to Andrew. Andrew Wiens is a senior water resources engineer with Associated Engineering. He specializes in hydraulic analysis and economic flood risk assessment for urban drainage infrastructure during extreme rainfall events and climate change. Andrew Wiens has been doing this work for over a decade. Again, we're very happy to have him on the line. He's going to be talking about a few case studies, or focusing on one case study in particular, and talking about a few others in British Columbia that his company has been working on. While we have everybody on the line here, I just wanted to remind you that our next webinar will be on February 16th. We'll have David Etkin in from York University to talk about an update of the hail climatology report he wrote for us quite a few years ago. He's been working on an updated document on this topic for us, and he'll present some of the findings on the 16th. So I understand that we have a pretty good audience today. One of the things we did last year, and I don't think we've done it in a few months, is if you happen to be in a room with a number of people watching the presentation, if you wouldn't mind just taking a second and use the question and answer box to just type in the number of people that are watching from your room. I understand we have about close to 100 registrants, but we understand many more people will be on the line. Okay, there's a couple coming in here. Thanks very much for that. And with that, so I'll pass it over to Andrew.
Great, thanks, Dan. So I'm going to talk to you about a case study that we did for the City of Surrey in BC. And just before we get going, the analytical techniques that we use for this project individually are not overly unique. Some of them are uncommon, not frequently used for municipal stormwater analysis. But the combination of all of these different techniques together for analyzing climate change and extreme rainfall is somewhat unique within Canada, but it's starting to get a little bit more frequently used. So what I'm going to do is I'm going to walk you through this case study, and while I'm doing that, we'll talk a little bit about the approaches and the numerical methods that we used, and give you an overview of the results and our findings. So first, we'll start off with a bit of an outline. So the whole project, the whole presentation is going to be geared around the City of Surrey Climate Change Rainfall Adaptation Strategy, which we completed about a year ago now for the City of Surrey. Now, within the presentation, I'm going to bring in a few more examples from projects that we've done with City of Burnaby, which have a level of similarity. And there's a few spots where I'll also talk about a City of Calgary project as well. Now, at the end, if we have time, I'll talk a little bit about insurance, particularly overland flood insurance and the disaster financial assistance program in kind of an example setting. And then we'll have a short summary and some time for question at the end. All right, let's get started with our case study. So this case study for City of Surrey, there was 4 project objectives that I'll just go over briefly. The main objective was to review the impacts of climate change across 3 different case study areas. And they selected 3 different case study areas for a few specific reasons, which we'll discuss shortly. The second point was to look at the performance of the stormwater system during rainfall events which may exceed or significantly exceed the capacity of the existing drainage system. So that would be the catch basins and the stormwater pipes that are buried below ground. And then following that evaluation, identify adaptation measures that might be needed to mitigate the risk of flooding as a result of climate change. And the fourth objective, which is an item that I'm not really going to talk about today at all, is the development of a screening level tool to assess and identify high-risk areas within the community. And for that objective, it was really geared towards looking at a city-scale tool that could be used to identify risky areas. So for those of you that are not familiar with the City of Surrey, it's located in British Columbia, in the bottom left corner, and it's located close to the ocean. Portions of the city border the ocean. The rest is either landlocked or bordering to the Fraser River. The city itself covers about 317 square kilometers and has a population of about 500,000 people. Now, unlike some of the other lower mainland municipalities in BC, City of Surrey has a significant amount of undeveloped area that's currently transitioning from forested or at least greenland type areas into new development. So they're in kind of a unique position where they're looking at new developments and trying to understand what to do with climate change. At the same time, there's a lot of existing areas that are being redeveloped. And this whole question about climate change and extreme rainfall has become quite important to them because they want to be proactive in their development approaches. So there's 3 different study areas, as I mentioned before. So I'm going to use my laser pointer. Hopefully you can all see this remotely. So the first study area is over here. It's relatively small, and that area consists of single-family residential housing that was built in the 70s and 80s. Quite a few basements, and it was built to a very different design standard than what the city uses currently. So it's a very different, level of service approach that they were expecting at the time relative to the standards that they design and construct for today. Area 2 is located over here. That is predominantly a new residential development area built to current standards. And they have a few basements, a few parkades, and that sort of thing. And then there's Area 3, which is located really close to Area 1. And that is a commercial multifamily housing area that's been kind of redeveloping over the last 20 to 30 years. There's a few basements, a few parkades, and that sort of thing. So the objective here was really to look at the performance of this system and look at, try to identify differences in performance within these areas to evaluate the need for looking at different types of historic developments in a different way. Okay, so prior to our study, the City of Surrey did a fairly detailed climate change analysis specific to rainfall statistics. So they engaged a specialized consultant to look at global circulation models, as well as downscaled regional circulation models. Take the data and look at the potential changes to rainfall as a result of a few different climate emission scenarios. So the results that they settled on in terms of their future design analysis are shown here on the screen. So they looked at 3 different timelines so that we could get an idea of how the risk of flooding relative to climate change affects the study area as a function of time. So looking at the 2013 rainfall data that they have, within the next 12 years or so, they expect to see an increase in rainfall, or peak rainfall intensity of about 20%. And looking forward to 2080, they picked 2080 really because if we were to design something and put it in the ground now, you would hope that the infrastructure you're building now would last about that long, possibly a bit longer. And the interesting thing here is that at that time frame, we expect rainfall to be almost 70% more intense than it is today. And that's a really important thing to take away from this, is that using today's standards, to deal with future performance relative to these types of rainfall events is going to be pretty challenging. So if the city is looking to get a certain level of service over the design life of that infrastructure, we need to not only account for the structural physical design constraints, but also evaluate and consider the climate change effects over that time frame. So why does this analysis matter? Unlike a typical engineering project that would evaluate drainage systems, the key point here is not to look at how big the pipe should be. The real objective here is to look at the impact to society when the drainage system is overwhelmed by a rainfall event that is significantly larger than the capacity of the minor system. So that's a rainfall event where the volume of rainfall and the duration that it arrives over significantly exceeds the inlet capacity of catch basins along a roadway, as well as the capacity of the pipes that are in the ground. So that would result in flooding. Now, from a big picture perspective, flooding along rivers and coastal areas is generally well understood by municipalities because floodplain maps exist. They've got technical staff that can manage that sort of development-related risk and so on. But rainfall flooding risk from extreme rainfall events is not so well understood. And part of the reason is that the tools required to analyze that have not been around for a long time. And the real issue there is it relates to software as well as computational capacity to analyze these types of events. They're not simple to analyze, and they can take a long time to evaluate with a computer. So that's why they're not done very frequently. So in a nutshell, flooding like this is what we're really trying to evaluate. We want to know, where do these types of flooding events happen, how often, and really what are the impacts. So we're looking at things like social impacts, potential for economic losses, that sort of thing based on current rainfall and the anticipated changes to rainfall as a result of climate change. So here's another example, and this one I've put up really because it also speaks to public safety. Extreme rainfall events do present not just an economic risk, but they do present a risk to the public as well. As a result of fast flowing water that's relatively deep. It's obviously a challenge for someone that might be stuck in that bus trying to leave. So that's another thing to consider as well. So I've showed you two pictures, and what I want you to take away from that is that it's not just an isolated event. These things don't just happen in a few spots in a big city. They can be quite widespread. So I've got a screenshot here that we took from a City of Burnaby project. And for that assignment, we were engaged to evaluate the effects of extreme rainfall events over the entire city. So this was a numerical model that we developed to look at an area that's probably in the range of about 200 square kilometers. And the objective was to identify overland flow paths and areas that would be at risk, whether for property damage or public safety, and find those flow paths. So we did that, and here's a static kind of picture of where the water flows. So you can see that there's an air photo with some blue, dark blue, purple, reds, yellows, and so on that are intended to signify the extents and depths of the water. So the very light blue represents really quite shallow flow, but it also shows you the concentration paths of this water when it's flowing through the community. So, for example, this area over here is relatively steep, and you can see that there's water accumulating in various locations. And under a pre-development condition, so that would be going back maybe 100 years or so in this area, you would have had a whole number of water courses that would collect runoff from rainfall events and route it down to a creek, and then that would flow off to lakes and rivers and ultimately the ocean. Now, development that's happened within the city, generally it tries to get rid of these overland flow paths because that's land that would otherwise not be developed if you left it green for creeks. So development approaches over time have obviously changed. New developments in an area like this would would be required to retain these water courses and so on. But in the past, that is something that was not done. So these risks from overland flows across the community do exist, particularly in older areas, and the impacts of this sort of rainfall can be quite extensive. So here's a screenshot that I've taken from I think it's Munich RE. It's a reinsurance company, and they had a nice little graph showing the last, I think, 35 years of weather-related loss events. So these are the number of events. It doesn't speak to dollars that were paid out or people that were impacted or anything like that. This is just a summary of the number of events that happened worldwide. And the green portion, which is the bottom end of each of these bars in this bar chart, represents meteorological events. So that would be extreme rainfall, convective storms, that sort of thing, which is really the type of extreme rainfall or the climate change risk that we're looking at in this study. So it clearly shows that the number of events like this are increasing as a function of time, and we expect that to continue. So here I've got a little slide that shows, and I think we obtained this from the Insurance Bureau of Canada, the top 10 events, and from that top 10, I just picked the ones that were flooding or storm related. There's 2 events that are missing. One of them is the Fort Mac fire, which is would actually be number 1, and that would fall kind of over here, as well as the Slave Lake fire, which would fall over here. The remainder of these events were either extreme rainfall or ice storm related hailstorm type events. So of those events, the top 10, as far as I can tell, 4 of them are related to extreme rainfall. So that represents a pretty significant risk, not just to insurers, but also to private property owners. There's a significant fraction of Canada that is being affected by these types of events already. So the goal here is to clearly look at these types of things and look for mitigation options. Okay, so that's kind of an overview of the project. Now I'm going to start talking about the components of the analytical tools that we use to evaluate these types of events. So the first one I'm going to talk about is the hydrologic model. So that is how we take rainfall data and convert it into a volume of flow that we can then use to size a pipe. So one of the things that engineers use to do this is called an intensity, duration, frequency curve, which is something I've got up on the screen here. So it's a graph that shows you on the vertical axis the intensity of the rainfall. So in this case, it's millimeters per hour, but it could just as well be inches per hour or per minute, however you like. And at the base, it shows you a duration. So for various clients have various different design standards. Every city tends to have their own approach for selecting a level of service standard. So for example, City of Surrey, their design standard is a storm that happens once every 5 years, 5-year return period. And that would be different than, say, City of Burnaby, which picks the 10-year and so on. So we would use a graph like this to go and select a design storm that we would use, and then we would put that into a hydraulic model and go from there. Now, one of the key points I want to make with this is that these intensity, duration, frequency curves that are used by engineers are based on historic observed data. So this is backward looking. It's not related to climate change. It doesn't look forward to the future to identify the potential changes. So that's a really important thing for people to keep in mind when they're designing and building this type of infrastructure or considering the potential impacts of extreme rainfall. Now, the other thing that happens is that these curves tend to be updated every 5 to 10 years. And if you put the graphs together for a single location, what you tend to see is that over the last 20 to 50 years, the rainfall intensity has been increasing already. So City of Surrey, for example, when they did their detailed study, they noticed that over the last 20 to 30 years, the rainfall intensity that they had been using had already increased by 20%. And that was something that they hadn't noticed in isolation for each of their curve updates because it was a small incremental increase, and that was attributed to just having more data or better data. The small incremental changes are generally not noticed. But from a big picture perspective, the effects of climate change have already been noticed for quite a while already. So one thing that we tend to use as engineers when we talk about rainfall or floods is something related to probability. So we tend to talk about these sorts of events either as a return period probability, flood frequency, or an exceedance probability, and they're really all intended to mean the same thing. What we're trying to communicate is how severe a particular event is and how often we expect it to happen, or what the chance of this event happening is in a given year. So for example, the 100-year flood or 100-year flood frequency would be defined as an event that has a 1% chance of occurring in any given year. Now, the 1% event also includes a chance of having an event that's larger than that, because that 1% fraction includes, let's say, the 1,000-year event and so on. So one of the key points that I'll make here is that this is an annual probability. So when you're looking at risk as a function of time or design life, it's not enough just to take the single design event and just use that, because if you're sizing a pipe for, let's say, the 100-year event, and you're hoping to survive in the ground for 100 years before it fails from a structural standpoint, not from a capacity standpoint, there's more than a 1% chance of that event happening over its design life. And in fact, it's actually a 63% chance that you will have the 100-year flood at least once during that design frame. So that's an important consideration for municipalities and others to consider when they're designing these types of infrastructure, that the chances of it failing over its design life is actually very high, especially when you're talking about the 5-year or the 10-year event. The chances of failure are pretty close to 99%. You're nearly guaranteed to have an event that's going to significantly exceed its capacity before it's replaced. Okay, so when we take this rainfall event, we need to convert that into a runoff volume. So the definition of that is really, get this rainfall, it lands on the ground, and the question is, how much volume do we get from that? Because some of the water will get stuck, it'll get infiltrated, it'll get stuck in terms of making things wet, and there's a number of things that influence that. So we have these special models that take all kinds of superficial data like soil types and soil cover, land cover, and so on. And all of that is combined and used to calculate a runoff rate for every collection point. So that could be the inlet for a culvert, the catch basin along the roadway, that sort of thing. And once we've got all of that, then we end up using some more software to combine all of these little hydrographs from every catch basin. And that's combined to estimate the required pipe sizes. So I've got a picture here from a project that, it's really just trying to show you that the end result of all this work is trying to size physical infrastructure that we can build to protect communities from these design events. Now, one thing I haven't talked yet about is about climate change and how that impacts our hydrology. So what we tend to do is we would look at, we pick our design event. So for this example, we picked the 100-year event, and that's probably a return period that we would use more for an event that would flood an area based on a river flood or a coastal flood. So without looking at climate change, we might have a study area where the frequency of flooding or the probability is about here. And depending on the level of development and the things that fall within a given floodplain, the severity in this case is nominally around here. Now with climate change, which is going to happen over a long period of time, the key point here is that the frequency of that same event is expected to increase. So instead of happening once every 100 years or having a 1% annual probability, we're expecting that that might, for example, increase to a 10-year or a 10% annual chance. So that just means it's going to happen more often. Now, over that time frame, which might be 60 to 100 years, let's say, the floodplain areas are probably going to get more developed. There'll be more infrastructure, there'll be more economic value. So as a result of that, the severity of the event will increase as well. So the net result of climate change and the timing and so on is that we're going to move kind of in this direction. So the adaptation tools that we pick are really intended to reduce the severity of this event when it occurs and get it down to a point where it's tolerable. Okay, so now that we've talked about how we get the runoff volume, let's talk a little bit about the hydraulic model. So this is the tool that we would use to look at what the water levels are, where we might have some surcharging or flooding in our study area. So first, I'm going to talk a little bit about the traditional approach that engineers would use in terms of analyzing this sort of a problem. So typically, engineers would really just look at the pipe system. So this is all of the buried infrastructure that's underground, it's out of sight, out of mind. And that system is typically called the minor system, and it does not include the overland network. So it kind of ignores everything that happens at the surface. Okay. So one of the assumptions that's built in this type of modeling approach is that the catchment areas are able to drain directly into this pipe system. So in other words, we assume that the catch basins they're big enough, there's enough of them and so on to collect all this rainfall for whichever event we're looking at. And what it ignores is any surcharge that goes back to the surface and might cause some flooding. So this model would allow surcharge to happen, but it won't give you any information about what the significance of that volume might be or where it might go. Okay, so when you have some surcharge, your model might say, well, we think the water level is going to be 0.5 meter or a meter above ground, but it does not account for the surface storage volume or the area where that amount of water might pond. So it's really giving you a false idea what that flooding might represent. And the reason that engineers take this approach is that the design goal for your design event, whether it's the 5-year event or whatever, is that the water level during this type of event is intended to stay at least below ground, if not within the pipe. So the whole idea of having surcharge to surface is really just a flag for you to go and fix something. You have to update a pipe or so on within your model, and then you take that, update your design plans, and off you go. So like I said at the beginning, the key objective with this assignment is to look at the impact of flooding. So this traditional modeling approach is not going to inform that question at all. So here's a picture, and it might be a little bit hard for people to see, but what I've got here is an air photo and a bit of an outline of where study area 1 is. And there's some black lines in here that represent the stormwater system in terms of where it's located. And then there's some nodes that represent the manholes along these pipes. And they're colored either yellow or green or red. And the red dots are intended to represent flooding, or at least nodes that surcharge the surface. So there's quite a few of those scattered around, and I'm hoping you can see them. They're probably at least 60 or 70% red. But what this does not show you is the extent of the flooding. So we know there's some surcharge, but we can't differentiate between a puddle and a lake that might flood 20 houses, for example. So that is the fundamental weakness of this traditional approach when you're trying to evaluate an event that's significantly larger than your design storm. Okay, so here I've got a quick picture of our study area 2. This is the newer development. There's a few red dots, but there's really not too many. So clearly a different level of performance for that one. Okay, so now I'm going to talk a little bit about the new approach that we've used to evaluate this case study. So there's a few things that this model is really trying to deal with. So what we want to do for this study is we actually want to understand if the collection system has enough capacity to collect this flow from the surface. We don't want to make the assumption that the catch basins are big enough or that there aren't necessarily enough of them. So we want to test that assumption. So our model actually has catch basins built into the model so we can evaluate that. And in the event that the minor system pipe is too small, so for example, it's surcharging for whatever reason, we want water to actually be able to flow back to the surface so we can evaluate the impacts of inadequate capacity at different points within the network. If we happen to have a significant amount of surcharge for whatever reason, this does happen on occasion, we may also get water coming out of manholes if those manhole lids are not sealed or bolted down or designed for pressure applications. Now, on top of that, now that we've got water coming to the surface, we really want to understand what happens to it. So the intent here is to have a tool that will allow us to understand the extensive flooding, where the water goes, and what it's doing. So in order to do that, so we took our minor system model and connected that to a very detailed overland flow model that will allow flow to follow topography. So it's called a two-dimensional hydraulic model. They're computationally expensive in terms of run times. They might run from hours to days, sometimes weeks if they're very large or if the storm is very long duration. So this is one of the key reasons that this is kind of an infrequently applied evaluation approach, and one of the reasons that, let's say 10 or 15 years ago, this was rarely used, if at all. These approaches were just not feasible. So the key reason that we're evaluating this is that we want to understand what the impacts are. Now, if you're a municipality, you would be asking yourself, well, why are we modeling this overland flow network? The whole design philosophy that municipalities and engineers use for municipal drainage is to have a drainage system that consists of two parts. One of those parts is the minor system, so that would be the catch basins and the storm pipes and the manholes. And the second part is the major system. So that is intended to be an overland flow path, and it could be a roadway, it could be a creek, or it could be a dedicated flow path through an area where water is intended to go during one of these extreme events. And the intent with this is to have safe overland flow conveyance for rainfall events that significantly exceed the capacity of the minor system. So if you're designing your pipe network for, let's say, the 5-year event, the major system is intended to deal with water safely up to, let's say, the 100-year event or possibly larger, depending on the study area and the risks and so on. So this modeling approach and this project is really intended to test this idea of the major system and whether or not it's actually safe, whether it's protecting private property from flooding and so on. Okay, so I've got a picture here that it's in Burnaby, and this is actually part of my commute to work. And because I'm a drainage engineer, I just happen to notice these things as I drive along. So along this roadway, there's kind of a low point or a sag, and that is typically where water would go because water likes to flow downhill. So if we zoom in a little bit, get a little bit closer, you can see that the sag is actually located at that location, and there's no place for this water to go safely downhill. Zooming in a bit more, this is the actual low point here. So testing this idea about a safe overland flow path obviously runs into a few hurdles once in a while. So for this project that we were doing for the city of Burnaby, we did our citywide model, found a few issues, and initially that was met with a little bit of skepticism. It's thought, well, we've got this design philosophy, things should be great. We shouldn't really have to worry about that. So taking some of these on the ground type pictures and looking at these low points, we were able to then take that back to the city and say, well, okay, so here's what our model is saying, and this particular sag is right about here. You can see that the model does correctly identify those types of issues and problem areas, and it's correctly flagging those problems. So that gave the client some degree of confidence in the numerical approach and this tool that we're using, really a screening level tool to look at these types of risks. Okay, so now we're going to step into some of the results from our City of Surrey climate change assessment project. So this is study area 1. It's the residential area developed in the 70s or 80s. And what I'm showing you right now is the flooding extents as well as the pipe network. So what you can see here is based on today's design storm. So that's the 5-year event based on the 2013 intensity, duration, frequency curve. Now keep in mind that the city found out when they were updating their climate change information that things had changed by 20 or 30% over the last while. So that's probably one of the reasons that we're seeing that this particular study area is already failing the current design standard or the current level of service that they're expecting their system to provide to property owners. So this really represents a significant amount of flooding. So for example, over here, we've probably got something like half a meter of water, if not a bit more, and that's flowing between houses or through houses to find its way downstream. There's a number of kind of creeks just on the other side of this road that you can't see right now. So on top of that, one of the other reasons we might see this amount of flooding is that in the 70s or 80s, when they developed this area, they may not have been using a 5-year storm as their design standard. They may have used something like a 2-year event, for example. So between climate change, changes to rainfall patterns, there's another element in here that we need to consider, and that is that municipalities sometimes change their design standards and they may increase as a function of time. So these older development areas or legacy areas would not be expected to have the same level of service going forward until those improvements are made. But at the end of the day, what we're really trying to figure out now that we know the flooding extents is we really want to know, what does this flooding mean? Is this material to our study area? And how important is it that we develop some mitigation options? So for that, we need another tool, because just looking at flooding extents isn't really enough to, I guess, quantify the scale of the problem. So knowing that we have 5 houses flooding versus 10 houses flooding is different than knowing the dollars of damage or the expected economic losses within these different study areas and different return periods and climate change horizons. So to evaluate that, we built another tool. So we have a economic flood loss calculator that we developed. It's based on, I guess, evaluation approaches that are used by the Federal Emergency Management Agency in the US, or FEMA, as well as common approaches that the European Union uses as well. So this isn't a new tool or anything like that. So what we're using for this is something called the depth damage curve. So this curve on the side here, on the horizontal axis, it's showing dollars of damage per square meter. And on this side here, we have water depth. So this gives us a quick tool for converting, let's say, this depth of water that happens to occur in this house. And this depth would be based on the water elevations that we would calculate from our numerical model and the building data that we have. And we can quickly apply that spatially for hundreds of thousands of structures on a floor-by-floor basis to come up with dollars of damage for a given study area and the particular design event. Now, what you need to do this with a reasonable degree of accuracy is you need a number of these depth damage curves. You need one for different types of development. You need curves for different floor levels. So for example, the main floor of a house that has kitchens and living rooms and bathrooms and all the rest of it could be very different than a basement level where you might just have, let's say, a media room and so on. Or if you have a basement suite, like that would be more like a main floor. You can have another kitchen. You can have some building mechanical things like a hot water tank, furnace, and so on. So understanding the variation in damage on a floor-by-floor level is important. Now, these curves, they don't just include the physical things like drywall and insulation and flooring damage. They also include content losses. And these are really they're based on averages, so it's not intended to be accurate for an individual house level. It's intended to provide you a representative number for a given study area. So it might be by postal code level or neighborhood level or project area, something like that. So this gives you a tool to get you a reasonably good number in terms of economic losses for a particular design event. Okay, so here's one important point that I would like to make. When you're looking at these models, what you're evaluating is an event that, for example, might happen once every 100 years. So that's one particular event, but it doesn't give you an idea of what the average risk is for a given year. In order to do that, you need to evaluate a number of different events that have a range of different probabilities, and then you need to calculate dollars of damage for each of those events. So you end up forming a bit of a curve here that represents that damage function. Now, the area under this curve represents the average annual loss, and it's a bit of a calculus, integral calculus type thing that we would use for that. And here's the formula. So it obviously looks kind of complicated, but don't worry, that's what consultants are for. So we would take that formula, all the results of our analysis, and combine that information so that we can calculate an average annual risk. Now, that number isn't just important for a municipality to understand kind of the day-to-day risk and what they could or should do about a particular problem, or trying to justify capital works to mitigate this risk. It also forms the basis of pricing something like an overland flood insurance product. That would represent the expected cost in terms of payouts for a given area. Okay, so now that I've talked to you about the different parts of our model, I'm going to get into the results and what we found. Okay, so just to briefly recap, so we talked about a few different time horizons. So 2013, so that would be today's design standard, even though it's 2018. And then, as we mentioned before, the City of Surrey looked at expected rainfall intensities for 2030, 2050, and 2080. And that's because 2080 represents the design life that you would hope to have based on an installation of something today. City of Surrey uses a 5-year storm, which has a 20% probability of occurrence in any given year, as their design standard. So their intent is to size a drainage system to contain and collect this rainfall water and put it in a pipe and take it away so that you don't have to worry about it. So we're looking at that 5-year event as a function of time with their existing system to see how that performs. Do they get the level of service that they would like to have? And then to evaluate the major system, we also used the 100-year event, which has a 1% chance of occurrence in any given year. And we looked at that as a function of time based on the climate changes that we're expecting. So there's 8 different, let's say, rainfall events that we analyzed. There's a few other ones that we looked at as well to do these damage calculations and calculate an average annual loss. But in a nutshell, that this is really what we're trying to do, is look at the changes in performance based on their level of service criteria and so on. Now, one key thing I'll mention is that for today, today's design standard, 5-year event, and the major system being the 100-year event, one of the things that was interesting is that the 2080 5-year event, so that's the design standard that they expect to have in the future, is actually almost equivalent to today's 100-year event. So the implications of that are very significant. So the frequency of flooding that they would expect to have would dramatically increase, and the effects of that would be very significant. So in the future, this 5-year event would really test today's overland flow paths. If they were not designed appropriately, there would be some pretty significant issues. Okay, so here we have area 1, it's the older residential area, and we're showing at the moment just the red dots for the 5-year 2013 event. So the question, like we said before, is we need a numerical approach to look at whether or not it matters. And without that two-dimensional overland flow model, it's very difficult to understand what those red dots really represent, what the flooding extents are, and so on. So this graphic here shows you the performance based on today's design storm and the existing system. Now I'm going to step forward to the 5-year 2080. So this is what would happen with the existing system if nothing happened up to the 2080 time horizon. So you can see that there's pretty significant flooding extents. A lot of these flooding areas start to connect, and you can see that there's these continuous overland flow paths that tie into existing water courses that you can see downstream. So this really, I think, reinforces this whole idea of past development that really didn't consider overland flow paths and past water courses, where they went, and so on. So these water courses that were basically put into a pipe, you know, they would flow overland, but that overland flow path doesn't follow a roadway. So there, in this case, there really is no safe overland flow path. And the consequences of that in terms of property damage are quite significant. Here we have results of the 100-year 2080, which really is just more of the same. Economic losses don't increase dramatically beyond the 5-year 2080 up to this one, because in a nutshell, it's all already flooded quite significantly, and the extents and depths are not changing that much. Okay. Area 2, built to current standards, is a completely different story. So here you can see the 5-year results. So this is their current design storm, and the intent, or the expectation at least, is that infrastructure that was built in this neighborhood should perform quite well during the design form. So this is really an independent type check of this existing system relative to the design approaches that are used. Now, we do see that there's some flooding in a few spots, but in general looks quite benign. So there's some flooding here, but that really just looks like some ponding, maybe a nice puddle on the roadway, and the impacts of that are really insignificant. And the economic loss calculation that we did confirmed that. Now, moving forward to the 5-year 2080 event. So this is today's level of service criteria with a future design storm. You can see that there's quite a bit more flooding. So for example, there's flooding that goes down this roadway and flows north in this case, and there's probably quite a bit of water on that street. What's not happening, however, is flow going through private property, with the exception of right over here. So this puddle that we were seeing based on today's event, so without climate change, was pretty benign, but with climate change, we would expect that this flow would actually go into this townhouse development area and ultimately find its way over here. And that did result in property damage losses and so on. So there are some impacts to this area as a result of climate change, but the interesting thing was understanding the differences between older design standards and current design standards. The issues here are generally pretty benign, and the improvements that might be required are quite small compared to Area 1. Okay, and here's the 100-year 2080. Again, much larger than today's design standard, but again, very little impact to the study area relative to Area 1 for the same event. So in a nutshell, that's really demonstrating that the mitigation approaches that we would consider for the city can be very different by development time horizon, as well as the design approaches that were used for these various neighborhoods. So it's really important to understand what the existing system is doing during these events, and to analyze that you need an effective tool to assess the impact of flooding during events that significantly exceed the design standards that you're using today. Okay, so we've talked about the flooding extents, talked about economic losses a little bit. Now we're going to talk about mitigation options. So when we got to this point in the project, we met with the city, and it was really kind of a brainstorming discussion to say, well, you know, we went through this study, we looked at all these different impacts, got a good understanding of what the issues are. What kind of approaches do we want to consider in terms of mitigation options? So I've got a list here, which is probably not complete in terms of things that we thought of. But for this study, what we wanted to do was limit it to a few different approaches and consider things that we would either would be our go-to option. So that would be something like, well, why don't we just put it in a bigger pipe and forget about it? That would be the standard operating procedure, if you will. And then we also wanted to look at some things that would not be considered, like modifying overland flow paths so that you can safely convey this water downstream. So it's not going to pose such a problem to the public, whether it's safety or otherwise. Another option was looking at minimum building elevations, and that's really examining a safe elevation to build to in different areas. So that would be a different level for throughout the study area. Now, one other thing we wanted to look at, that was really because developers were pushing back a little bit and saying, well, you know what, your building code requires these backflow preventers. We don't think they're necessary, and we really just don't want to put it in. So the city asked us to look at that one specifically for existing and for, I guess, kind of proposed developments to see what the payback might be if you're a property owner in terms of that sort of improvement option. So the items shown in red here are the improvements that we consider for this project. Okay, so one of the items we talked about, as I mentioned, was sewer backflow preventers. So, and just to be clear, when I'm talking about sewer, I'm really talking about storm sewer, not sanitary or combined sewer backups. The assumption in this area is that the houses have perimeter drains and that these are connected to the storm sewer system directly, so that high groundwater levels or roof leaders that happen to be connected to these perimeter drains are drained directly to the pipe, and this water is sent away. And the second assumption was that these pipes do not have an existing backflow preventer on it, and that given that it's an older neighborhood and things have probably settled a little bit, there's a risk of flooding basements as a result of either cracked foundations or installation of other connections to these perimeter drains, whether it's for a sump pump or otherwise, that presents a potential intrusion point for surcharged stormwater to get into these basements. So we did that analysis, did all the economic loss calculations, and we came up with a benefit cost ratio, and it varies between the study areas between 200 and 400. And that's based on an estimated $5,000 cost to retrofitting the existing structure. And the ratio seems pretty good. One thing I want to caution, though, if you're trying to take these numbers to use them for something, these benefit cost ratios seem, say, unusually high. It's higher than what I've seen in other projects and other study areas. There's probably two reasons for that. One is that for this particular assignment, we did not have a solid understanding of how many houses had basements or what the connection type was or the past performance. So this vulnerability and the presence of basements was largely assumed. So that affects your losses, which kind of magnifies your benefit cost ratio. The second issue is that this study area is located near the top end of the watershed. So there's very little overland flows coming in from elsewhere. And if that was the case, it would really, really lower that benefit cost ratio, because you would just closing off the pipe and preventing the sewer from backing up into the basement would not provide any benefit because of overland flows coming in through window wells and so on, and flooding basements. So that's probably another reason that these numbers are quite high. Now, this sort of improvement is pretty easy to implement, provided you've got property owners that are keen to do so. And that's a good thing in terms of risk mitigation, but again, you've got to have buy-in from private property owners. Okay, so the next item we looked at was upgrading pipes. So this is kind of a standard approach for municipalities. You go and do a new development or redevelop a neighborhood. All of the water, sewer, sanitary pipes would get resized to meet current standards and so on. So the intent here was to get a bit of an understanding of what would it take to achieve that based on current standards and the climate change information that we know of already. So for that assignment, we looked at the areas that would require improvement. And you can see the pipe network here in this picture, and the pinkish colored pipes are the ones that would have to be replaced to meet the current design standards. The green ones are the ones that are okay in terms of capacity, but not necessarily in terms of design life. So some of these pipes might be, they might already be 50, 60 years old, and you'd want to replace them anyways. But the point here is that you wouldn't have to replace them purely because of inadequate capacity. So this analysis was done for the 5-year 2080 event. So that's the performance that we would hope to have at the end of the design life of this proposed infrastructure. So based on the flooding that would be mitigated with that type of improvement, the benefit cost ratio in this case is between 15 and 50, depending on the study area. Now, again, these numbers seem a bit high, and for this option, I think the key issue here is that the downstream receiving environment is really just across the street. So we don't have to carry this water for kilometers and kilometers to a safe discharge point like a river or a lake. And that's something that significantly impacts these benefit cost ratios. For large scale projects that are more than just neighborhood level, these numbers are usually in the 1 to 5 type ratio. So this is again a bit atypical, but it does demonstrate that this approach does have some value. Now, one of the things that you don't get from this is protection from overland flow events. So when you do have an event that exceeds your 5-year 2080 event, whether it's tomorrow or near the end of its design life, there is still significant residual risk that remains. So that's something to keep in mind. Okay, the next thing we looked at was a minimum building elevation strategy, and that was really asking the question, if we want to do nothing to the pipe network in terms of upsizing pipes and adding capacity, and we don't want to worry about the overland flow path, so in other words, let's just let things flood, how do we avoid property damage to houses? So the answer to that question is really, how much higher does the, let's say the main floor elevation have to be above average ground elevation to avoid that? And by extension, that would mean that you wouldn't have something like a basement below that main floor level. So the analysis found that there's quite a few houses that wouldn't have to be raised by much. So somewhere between, let's say, 250 millimeters or 500 millimeters, but there's also quite a few that would have to go up significantly in the order of a meter or so, which is really not practical in many cases. It's difficult to do that. You lose a lot of development space if you're a property owner. That means you're losing your whole basement. You got to lift your house, or conversely, you might only be able to have a single floor as opposed to a 2-story house with a basement because of height restrictions and so on. So this strategy creates a whole number of issues. In terms of implementation, we looked at what would be required for the 100-year 2080 event. So this is looking at a much larger event than just a 5-year storm. And the results of that, we came up with a benefit cost ratio of 15 to 80. And that's really based on a slow redevelopment process. It's not going in tomorrow and what would it cost to fix all these houses. It's really premised on a building permit type improvement scheme where nothing in terms of improvements would be triggered on the property owner side until somebody came and said, well, this house is really old, I want to build a new one, here's my permit application, and then the city would turn around and say, well, actually you're in a risky area, you need to do this to reduce your risk. So the costs are fairly low for that type of approach. Now in terms of cost, we're not counting potential lost revenue as a cost because you're losing space. We're just thinking construction cost. Now that approach is a long implementation time horizon, so it could take a long time to implement this and redevelop within a neighborhood, unless the city is looking at, let's say, redevelopment incentives, or developers are looking to densify these types of areas, in which case you can start from scratch again and do that quite easily. Another option we looked at was modifying overland flow paths. So the question for that is, what do we have to do to make this water flow safely downstream to these water courses so that there is limited or no damage to private property? So this option was really kind of a combination of the minimum building elevation approach and purchasing properties at key points so that we can create a continuous flow path and lower water levels so that we don't have to raise private property by more than a key amount, let's say half a meter or so. So that was an interesting analysis. We found that we would have to buy quite a few pieces of property, and in Surrey the main cost for buying property is land. So each of these houses are probably in the $1 million range just to get the land. Now again, for this one, we looked at the 100-year 2080 event, and the benefit cost ratio is in the range of 15 to 80. So again, this is pretty similar to a pipe option, except that you get a much larger degree of protection. You're also looking at the major overland flow path event, that really extreme event that we hope that doesn't happen. But this also looks further ahead. So it would allow you to maintain a minor system together with a major overland flow path that fits today's design standards. So it's a bit of a more of a, let's say, a holistic design approach that meets the development ideas that municipalities have today. But again, it's a long implementation approach. Okay, so Dan, I think we still have a bit more time. If we're running short, this is a section that I could skip. If you don't chime in, I'm just going to keep going here. It might be another 5 minutes. Okay, so we'll talk a little bit about overland flood insurance and disaster financial assistance programs. Okay, so about a year ago, I got my little notice in the mail from my insurance company saying it's time to renew, and surprise, premiums are going up a little bit. And by the way, read this letter from Emergency Management BC. So that's an agency in BC that deals with impacts of extreme, whether it's flood events or fires or what have you. They're kind of an intermediary between private property owners and the federal government when the Disaster Financial Assistance Program is activated. So I was generally aware of this sort of thing, but one of the things I found interesting was that this letter was really intended to inform people that if there's no insurance product available, then you could use the Disaster Financial Assistance Program potentially. But what it's really saying in this case is that, you know what, you can buy this overland flood insurance, and if it is available, you're not going to be able to get reimbursed. And another key point that they made was that reasonably available should not be confused with affordable. So if I was to, let's say, live in the floodplain, this premium might be very expensive, whereas if I lived somewhere that's less risky, maybe the premiums would be quite palatable. So in a nutshell, what they're really trying to convince me is, you're probably on your own because people in your neighborhood can buy this overland flood insurance. So that was interesting. But shortly after that, I decided to move to Calgary, where I am now. And given that I've been doing this extreme rainfall stuff in Calgary for the better part of 10 years, I really had to think a little bit about that in terms of, well, where do I really want to live, and do I really want to pump out my basement every other year? So what I did, because I'm an engineer, I went and took the area that we were interested in moving to, mostly because of proximity to the office, and started eliminating areas that I didn't want to live in. So the easiest thing to get was floodplain mapping. So the province of Alberta has this sort of data. Most provinces across Canada are like this. Major cities would have some type of floodplain mapping, but it might be dated, it might be recent, and so on. So it gives you a bit of an idea of where the risk is purely from river flooding. What you can't get is an understanding of flood risk areas from extreme rainfall. So because I know how to do all this stuff, slow Friday nights, I build my own model and look at flooding extents. So based on that, I've got a pretty good idea of where these risks are, but this is really information that's not available to the general public, because these types of floodplain mapping information, it really doesn't exist. This is a very new thing in terms of municipal risk assessment. And the key point that I'd like to make here is that, the techniques that we're looking at in terms of the City of Surrey project is really something that can be applied to very large areas. It's not overly difficult to do, and as a screening tool, this can be quite effective. Okay, so time for a really quick summary. Okay, so first thing here, overland flow. What I like to tell municipalities is that we shouldn't just assume that this overland flow is safe. And if you're an insurance company, you probably don't want to assume it's safe either. You really want to understand where these risks are. Another reason is that it's not necessarily always a problem. And in some cases, there's actually really simple fixes. So in this case, there was an option to build a really small berm here to deflect this water and make it flow north into a detention pond where it was really supposed to go anyways. So cheap fix mitigates a whole bunch of flooding damage to these townhouses. And that's it for me. We're on to the questions.
Thanks, Andrew. Dan, questions?
Apologies. It's Dan here. Andrew, that must have been a very slow Friday night. So we got a few questions here from the online attendees. Actually, a number of questions about the climate change projections. I understand that this was a separate study that was done by Surrey, but could you provide a little bit more information about how they were about how these figures were developed? Specifically, you mentioned that you're looking at the 5-year and 100-year return period events for your models, and were these increases in intensity, did they apply to both the 5-year and 100-year return periods?
Yeah, that's a good question. So I've got let's say a general understanding of the process that was used. So the numbers that I showed in that chart, I think they really just apply to the peak intensity rainfall. So it's probably the 5 or the 10-minute time of concentration, and not necessarily across the entire storm event. But for these types of extreme rainfall events, it's the peak rainfall intensity that it really influences the degree of damage. In terms of how those were developed, they had a professional meteorologist and some climate change gurus that put that together. So I'm a bit fuzzy on the process for doing that, but I think the changes are relatively consistent across the board for the different return periods.
Okay, thanks. And there's also quite a few questions about the depth damage curves that were used here. Were these based on the Alberta curves? And first of all, I guess, where did the information come from to develop the curves? Was it modified to match the case study? And also there are some questions about, you know, whether it was all economic damages that you're looking at, or did you consider non-economic impacts as well, say things like things that wouldn't normally be included in these kinds of studies, like health costs, emergency management costs, and that sort of thing.
Yeah, okay, so a bunch of questions there. Okay, so the simple answer to that is that the depth damage curves that we used are generally based on the province of Alberta's rapid flood damage assessment tool. So there's a whole number of different curves. They're very detailed. So for this project, we made some very generalized versions at averaging a variety of different finishing types by land use and so on. So instead of having, let's say, 5 different single family curves, we just had a single one that was intended to be an average representation of all of them. The economic losses were just structural damage and contents, so it did not include any of the other social impacts like health and environmental losses, consequential losses, and so on. So a fairly high level assessment, I would think.
Okay, thanks. And there are 3 questions here from 3 different people about the model, the 2D modeling, the modeling that you had been using. Which package did you use? Was it expensive? What would you recommend for another city looking into this type of work?
Sure. So for this project, we used software produced by DHI, Danish Hydraulic Institute, and the software package is called Mike Flood. And what that tool allows you to do is take a minor system model called Mike Urban and another one called Mike 21, make them talk together so they can dynamically exchange flow information and water levels at every time step. That software is fairly expensive. I think you'd probably be looking at something like $80,000 or so to get in the door with that software package. But you don't necessarily need to use that one. For smaller scale projects like this one, you could probably use PC Swim 2D. I think that one would be fine. And the cost for that, I think, is quite a bit lower, although I'm not entirely sure how much. It might be, a few $1,000s, so substantially less than Mike Flood.
Okay, thanks. Also some questions about the basement elevations for the economic impacts. It sounded like a number of assumptions were made about basements. So was there any work done to assess the height of the ground floor of the buildings or basement floor slabs?
Yeah. So the general approach that we did was that we would start off by estimating the main floor elevation for different land use types. So for residential, for example, I think we assumed an offset of either a foot or half a meter between average ground level at the perimeter of their house and the main floor level. And then the standard floor height that we used was 2.5 meters. And partway through the study, the city thought, well, let's go and double check that just to see if it seems rational. So they went and looked at, building permit information and plans and so on. And that number seemed pretty rational for this study area. So we continued to go with that. Now you could obviously get much more detailed data if you had the budget to go and collect better data.
Okay. And so I guess they did a sample study of building permits, or is this something that's not? Yeah, okay. So for the most part, the building permits would include this information. There just wasn't resources to go through every single permit and evaluate the height.
That's correct, yes.
Okay. And another question related to that. So for the backwater valve CVA, there was an assumption that your foundation drainage was draining into the storm system. Again, is this something that the city had been tracking? Was there a policy about this? Or was it a safe assumption that everybody had this type of connection?
Yeah, that's a good question. I think this was something the city was, I think, more concerned about on maybe a go-forward basis. You know, a lot of the older developments, you know, we looked at flooding records and flooding complaint data for Area 1 where we were seeing all of this flooding. And one of the things that came out of it was that there was really very little flooding complaint related to basement flooding. So that really made us question that whole idea a little bit. And the city's perspective on that was kind of two-part. One, they thought, well, you know, given that this was developed a long time ago, they thought maybe people actually had, you know, cellars or something like that, or they had, lost the word here, but sump pumps, sorry, that's what I'm looking for, would have sump pumps, and they actually pump the surface instead of directly to the storm sewer. So maybe people have already dealt with this issue, and you know, they've moved on, and the city just hasn't quite caught up to what people are doing. But one of the more common things is that people are going in and retrofitting things, and they don't want, you know, sump pumps to discharge the surface if they're a new property owner. So they're creating that risk when they do renovations or build a new construction. So they really wanted to get a handle on that more from a, let's say, go forward basis than what was happening here in the past.
Okay. So another question. So you had a number of maps there for future rainfall intensity scenarios. I think specifically in the newer subdivision that you looked at in Surrey, where you're showing that under climate change scenarios, the overland flow routes were performing well, and there wasn't much surface flooding. Could you make was there any discussion about what might be happening underground? And I'm thinking specifically about, you know, incidental connections between storm and wastewater systems, I&I, and that sort of thing. And if that was a consideration. So, you know, perhaps you have no visible surface flooding, but basements are being flooded in another way.
Yeah, that's a good question. So we assumed that there were, just for the sake of simplicity, that there was no cross connection, but that's a valid thing that should be checked, and you would typically analyze that way in the field with different means, like a smoke test for sanitary sewers to see where it comes out. For this project, for Area 2, we did have a close look at that particular issue in terms of basement elevations and so on. And one of the things we found was that the new design standards actually requires that the water level in the pipe during this design event is actually maintained inside the pipe, and that the basement elevation has to be, I think it was ½ a meter or so above the connection point. So there's two kind of degrees of, I guess, flood mitigation there. They're trying to keep the water in the ground, and they're having this kind of vertical separation to reduce that risk.
Okay, thanks. A question from, well, the Southern Ontario Municipality. Kevin, let me know if I got your question, misinterpret your question here, but the question is about the minimum building elevations. Can you clarify, provide more detail on the minimum building elevation approach? What assumptions were made for ongoing development? Was there any consideration of future development, perhaps infill development, or were you only considering the existing properties?
Yeah, that's a good question. So I'll try to answer that one maybe in a slightly different way. So the things that you've mentioned, like redevelopment and infill and so on, these are all important things to consider when you're developing a minimum building elevation approach. So every time you incrementally fill in a particular lot because somebody wants to either mitigate flooding on their property or is kind of told by the municipality that you must be above elevation X, what you end up doing is you're deleting some floodplain storage for each lot individually. So as you move forward, that minimum building elevation number could actually creep up depending on how you've done the analysis. So for our approach, what we did is we took all of the private property areas and we artificially raised them by 2 or 3 meters purely to force all of the water to stay within the overland flow paths, which are generally roadways in this case, to see what the maximum elevation would be if we allowed absolutely no storage or flow through private property. and then that was used to estimate the required minimum billing elevations for those study areas.
Okay, thanks. So there's a follow-on question to the discussion about model selection and cost and so on. So again, from Southern Ontario Municipality, question from David here. Can you give a ballpark estimate for developing these types of the overland flood models, specifically, say by hectare, square kilometer, something like that, in a moderately populated suburban area? Say, you know, a value per square kilometer, or hectare, something like that.
Okay, so it sounds like you're looking for a dollars per square kilometer type approach.
Right.
Yeah. Okay. That's a good question. So I've probably built, I'm going to guess 20 or 30 of these models, and I find the most time-intensive portion of this exercise is building the minor system model and getting that to function to a point where it represents observed information. So it'd be a kind of a calibration type event. And the biggest challenge there is usually municipal data in terms of being complete with all of the required attribute data. So that could be things like invert elevations, pipe sizes, connectivity, whether the pipes are snapped to the connected manholes. And in rural areas, understanding the drainage network in terms of ditches and culverts and water courses is even more of a challenge, because we need cross-section data, which is typically not retained within municipal GIS data sets. So that would be something that would have to potentially be field collected through survey. That would rarely be something that we could obtain from aerial topographic data like LiDAR. So in a nutshell, can I put a good number to it? Probably not. I think you know, if you're looking at something that's in the you know, 50 to 100 square kilometer range, you could be, and it really depends on the level of detail in terms of analysis, number of mitigation options, number of storms that you're analyzing. You know, you could be in the range of, let's say, 200,000 to 800,000, depending on input data quality, level of detail, and that sort of thing. So, you know, happy to have that conversation offline if that's something of interest. There's a lot of things you can do to influence the cost in that type of analysis.
Right. Okay. Good point. And hopefully we'll be able to connect you guys after the presentation. A question about the future, or the climate change projections, and I guess the study in general. So the purpose of those projections in the case of this study was to look at the economic impacts, and it's sort of a, you know, an exploratory study of climate change impacts. That's my understanding. Is there an intention to apply those climate change values for infrastructure design as well?
Yeah. Yeah, so I think you got the intent right. The purpose of the study is really to provide some information that the city can use to guide their decision making going forward. I do think the intent here is that they would use the climate change data as part of the design for new work, because, you know, they really would not like to have to replace pipes or other infrastructure before its useful service life ends, just because it's too small. The cost of doing that is very expensive. So that, I think that's where they're going to go with it. You know, have they defined exactly what they're going to do yet? Probably not, but I think they're getting close.
Okay. Another question, well, on the historical data. So you mentioned early in the presentation that they had looked, Surrey had looked into the historical change or change in IDF curves based on historical information as well, and it compared older IDF curves to more recent ones, and it found a 20% increase in intensity over the past 20 to 30 years. So you've done a number of studies in Western Canada. Is this a consistent finding, would you say, across in that area?
Yeah, that's a good question. So the work that I've been doing over the last 10 years or so in terms of extreme event analysis and so on, I think that applies a bit more to the analytical approach. The climate change analysis itself, in terms of looking at changes in rainfall intensity, that's a bit newer, but looking at other municipalities, we tend to see that the degree of change is different, and I don't have a good number to give you for other areas, but I think the trend is there. So, for example, a lot of the work that I've done in Alberta and Saskatchewan, the trend tends to be that municipalities are contacting us on a reactive basis because they've experienced a 100-year event and there was some significant property damage, or they've had 2 or 3 100-year events in the last several years, which statistically would be quite unlikely, unless you were considering the idea that, well, maybe this 100-year event that we're getting from this old IDF curve is actually not a 100-year event anymore. Maybe it's now a 10-year event, and so on.
Okay, maybe one final question. There's still a few questions online here, but if you've got Andrew's email address, maybe you can follow up with him afterwards. So one last question is about the map. So you have a number of maps of specific neighborhoods in your presentation. Have these been made available to the public in Surrey? And you also had a map of Burnaby, it was Burnaby, I believe, where you'd identified overland flow routes in some of these older neighborhoods. Have these maps been made available to the public? And if so, has there been, what's the public's reaction been to these maps?
Yeah, good question. So I can only answer one of those. The second one about public reaction, I haven't got any feedback yet from the city, but it would be good to get that and have an understanding of it. In terms of making it public, I believe the City of Surrey data, now that it's been finalized, is available to the public, but you might have to know what to look for or where to get it. Although the city has been pretty proactive in advertising it. There's been a number of presentations that they've done and so on, so they're not trying to keep it quiet or put it under the rug or anything like that. One project that's maybe an example of public reaction, there's a City of Edmonton had a citywide flood mitigation assignment, and there's a bunch of stuff in the news. If you Google it, you can probably find some information about it. And I think there's a pretty wide range of public reaction on that one.
Sure. Okay. Thanks, Andrew. This was a very good presentation, very interesting, and also very well attended. We had well over 100 people on the line here. So before we sign off, Andrew, any last comments?
No, I don't think I have anything left. Thanks for tuning in.
Okay, thanks again, Andrew, and thanks again, everybody, for joining. And just a reminder that the next Friday Forum will be on February 16th, and we'll have David Etkin from York University who will be talking about hail in Canada. It's an update of a study we had done with them over a decade, I think about a decade ago, on Canada's hail climatology. So check your inboxes for the invite for that event. And thanks again, Andrew, and we'll talk to you everyone next time.